Okay, so welcome to the first of two modules that we're going to give you as a part of the ACM Summer School in Data Science, which covers probability and statistics. And so this, along with what Professor Sridhar would have covered in linear algebra and optimization, should hopefully give you the basic mathematical foundations for data science. Yeah, I mean, I guess you would have already figured out when we covered the linear algebra and optimization that we're trying to cover what is usually covered as individual courses into single lectures. Hopefully, this won't feel as much of a crash course because, again, I'm certain that almost most of you would have at least had a single course in probability and statistics. So we are going to try and treat this as a little bit of a revision. But I am also aware of the fact that it's being spread over exactly 2 sessions. So I'm not going to be hyper ambitious. I am going to keep the lecture level at a fairly basic level. So some of you might find it elementary, but that's fine. The subsequent sessions I know are going to be fairly advanced. So for some of you, at bare minimum, this should be something that you can accomplish. Okay, so why probability and statistics? The obvious answer has already been given, which is you're going to use a lot of it in data science, probabilistic modeling and statistical inference. But I always have another motivation to teach this because I somehow feel that whenever a problem statement comes to your doorstep, whether it's in the form of a business problem or whether it's in the form of a research problem, many of them actually entail the use of only probabilistic modeling or statistical inference and nothing more fancy. So sometimes, we all get caught up with a whole bunch of buzzwords, but staying true to the problem statement might mean that you're actually only using probabilistic modeling or, statistical inference. So in that sense, I also think it's a great tool to have in your toolkit. So I'm going to break the 2 sessions broadly as basics of probability theory, just give you the basics of probability theory in the first session. In the second session, we'll talk very briefly about descriptive statistics and mostly about inferential statistics. Okay. So what are we trying to do today? Already, I think this is ambitious. I'm going to give you a very quick intro to probability, probably taking about 10 to 15 minutes. I'll spend a little bit more time on overall talking about random variables, and I'll try to get to derived distributions and joint probability distributions. This is purely out of greed. I usually like to talk through a few distributions and their functional forms, but I know that's just not going to be possible given the time. I just have them as a backup. Okay, so let's start. Even before we can even talk about probability, we should just start with some very basic understanding. Again, for many of you, this is fairly basic, but I want to start from the very beginning. So let's first define something called a random experiment. Okay, so a random experiment is an experiment that can result in different outcomes, even though it is repeated in the same manner every time. Okay, so I can give you a couple of different examples. Imagine you go to the balcony here or lean out of the window and you drop a ball. And your friend below is kind of with a stopwatch, and he's going to measure how long it takes to get to him, right? Now, this is a classic random experiment. Because each time you repeat it, you could potentially have different outcomes. And so there is a random component to it. And yes, you can argue saying that the more and more precise I get about how I repeat the experiment, the less variability there is. But nevertheless, if there is some random component to it, the way the breeze is blowing, the way you shout and say, hey, start, and even without getting into relativity and things like that, quite simply put, there is a random component to this experiment that's going to lead to different outcomes if done at different times by different people. And we are very interested in studying this random component. We want to quantify it, we want to model it, and further down you might want to predict it and so on. Okay, so that's the premise for something called a random experiment. It can have different outcomes, and the random component leading to the different outcomes is what we're going to study. Okay, I'll give you another example. So another example could be, for instance, we're going to have a tutorial today evening. The number of students who will get tutorial question number 3 correct. So imagine the answer is a true or false, or basically there is a yes or no kind of a condition. How many of you will get that question correct? Now, this is a little different, right? Because here it's hard to think of repeating the experiment multiple times. You can. But what I'm trying to quantify is not the fact that when you repeat it, it will have a different outcome, but the fact that before I give this exercise out, before I do this experiment, the possible outcomes are still random from my perspective. Right? So these are two very interesting ways. So there are two things that I wanted to highlight. First thing that I wanted to highlight is that dropping the ball is what we would call a continuous sample space. So it takes some amount of time, and the time can be anything within a particular range. We're going to go a little more deeper into that in a few seconds, but imagine it takes between 10 to 15 seconds. Between 10 to 15 seconds, technically, it can take any precise amount of time. Of course, understanding that a stopwatch might stop with some milliseconds, but that's the problem with a stopwatch. It's not a problem with the fact that you could have anything between 10 to 15 seconds. Now, flip to the other side, which was the experiment that I spoke about, which is how many of you will get question number 3 correct in today evening's tutorial. There, the answer had to be, it could not have been -1. It could not have been 500, because there are only 30 and odd people in this class. So it could not have also been 3.5, right? So this is what we call a discrete sample space. So the two examples I've given you, one thing I wanted to highlight is the continuous sample space versus discrete. Both of these are random experiments. The other thing that I wanted to highlight is your conception of a random experiment. You can quantify that random component by imagining that if you had repeated it, you would have had different outcomes. The other way to kind of imagine this is to say, the plan is that even if you repeated it, it's probably the same, and repeating it doesn't make sense, because I give you the question once, I tell you the answer, what does it mean? But the fact that before I actually go do this, from my perspective, it's random, because I don't know how many of you are going to get the answer correct. Okay, so I've already kind of covered sample spaces. It's basically the set of all possible outcomes of conducting a random experiment, and that's called a sample space. Okay. Now, I'll give you a simple example, and we'll try to keep this example just so that we can use it going forward. So imagine a thing of answering 5 tutorial questions. So I give you 5 tutorial questions today, and the TA gives it to you sequentially, one after the other. And we are interested in what you get correct, right? So what would be the sample space in something like this? So the TA actually comes and says, question number 1, and we talk about it, some of you write it. So let us take one person, and let's say from their perspective, the random experiment is what they get correct in the tutorial. Then you would have to actually start with the first question, right? You would have to start with the first question, and the person probably got that correct or wrong, right? But then once they got that correct or wrong, what happens in the second question? So that kind of splits up. And you do that all the way for all the 5 questions. And what do you have? You'll have a sample space of some discrete possible outcomes. I've given you an example of a discrete sample space. And you'll have it in the form of what I have in this slide, which is like y, 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 n, and so on. Okay? We'll talk in a second about how many such combinations exist. So this is one classic example of a sample space. Okay? Now, of course, you can reframe this in different ways. Now, suppose you only cared about the number of successful answers you got, and not which ones in particular that you got right. Now, the sample space is going to look very different. Right? Now, the sample space is going to be just 0, 1, 2, 3, 4, and 5. Okay? Okay. So now that we have some feel for discrete sample spaces, we'll use these examples going forward. Let's define what an event is. And an event is basically a subset of the sample space of a random experiment. So all possible outcomes, if you take all of them and you take a subset of that, that subset can be just a single outcome. It can be multiple outcomes. But as long as it's a subset, that's what we call an event. So an example of an event in this kind of a setting would be something like getting exactly 4 questions out of 5 correct, right? When I had the sample space written out as y, y, y's, and n's, there are multiple ways I can get exactly 4 correct, right? So I can do, basically, since this is a subset, and I'm dealing with subsets, I can do everything that's related to set theory. I can find out unions, I can find out intersections, I can get the complement of a subset, and all of that will answer some very useful questions for me in this perspective. So in this particular example, I say, what is the union of getting 4 questions exactly correct? So that's one set. Getting 4 questions exactly correct is one event, because it's a subset of particular outcomes. And then you have another subset, which you can call as getting exactly 5 correct. That, fortunately, has only one outcome in it. But I can take the union of these 2. Now, why would I be interested in something like that? Because it answers a very different question. It answers the question of, getting at least 4 out of the 5 correct, right? And that could be a very useful thing for us to quantify and understand. Okay, and another useful definition is that when two events share nothing in common, that's what we call as mutually exclusive. The intersection is basically null. Okay, couple of other very useful concepts to jog your memory with respect to probability and understanding random variables is sometimes the sample space is very obvious, right? So it's just some set of discrete things, and you can just look at it and you can just enumerate it. But sometimes you have to actually list them out. So for instance, in the case of the YYN, getting the first 5, we actually tried to say, well, the first question can be right or wrong. That's two outcomes. But then the second question can be right or wrong. That's another 2 outcomes. So you totally have 4 outcomes. Now extend that same logic. How many possible outcomes can you have for all 5 questions? 32, right? So you do 2 times 2 times 2. So a lot of the basic idea is enumeration through multiplication is often a very convenient tactic to understand the sample space. 2 other very pertinent ones to have in your toolkit is permutations and combinations. So suppose you instead, if I change the problem to say the order in which questions are attempted, I no longer care about whether you get the questions correct or wrong. I really care that I'm really curious. The TA says today we are going to cover 5 problems, and she hands you the sheet similar to yesterday. And what we're interested in understanding is what is the order in which the questions are going to be attempted. So is it going to be question 1, 3, 4, 5, 2, or what is the order? How many such possibilities are there? And a simple, fairly elementary math can show you that this should be n factorial. So suppose you had 5 questions, it will be 5 factorial, which is nothing but 5 times 4 times 3 times 2 times 1. Because the first question, any 5 of them are possible. Once the first question gets fixed, there are only 4 more remaining, so you do that. Okay. Now if you have a subset, suppose you had saying, she says only 3 need to be attempted out of 5. Okay, but she still cares about the order. We still care about what 3 is done. You'll have it of the form factorial by n minus. Another very useful toolkit and conception is through combinations. Here we are saying we don't care what order in which you attempt the questions, but we really care which 3 questions you chose out of 5. Right? So suppose I'm interested in knowing all the possible solution packages that can be there. Which 3 out of 5 get picked is another way of describing the sample space depending on the question that is asked, and combinations are very useful for that. And again, combinations can be neatly expressed in terms of n factorial by n minus r factorial times r factorial. So what is n and r out here? So I'll give you 5 questions and I say any 3 questions you're going to attempt. You can do that and you should be able to get an idea of the sample space. Okay. Now we've done basic definitions to the point where we can talk about probability. So I'm going to first talk about the simple discrete version, and then after that we'll expand that to continuous. So you can think of probability as the likelihood or chance that a particular outcome will occur from a random experiment. Okay? It is reflected by assigning a number between 0 to 1. Many people like to talk about it as a percentage. Now, you can extend that probability of an outcome to the probability of an event. Okay, so probability of an event, denoted by P of E, is the sum of the probabilities of the outcomes in E. So I can basically take an event. Let's take the example that I gave you is getting exactly 4 questions correct. You know there are multiple outcomes that belong to that event. If you can take the probability of each of those outcomes and start adding them, you have the probability of the event. Okay. So some basic axioms that you will probably have to know and remember. And many of these should be extremely intuitive and familiar to you already, is if you can think of the sample space as S, okay, and you can think of A as an event, then first of all, probability of S is equal to 1, okay, which means you take every possible outcome and you sum the probability of each of these outcomes. The probability of the entire sample space is 1, okay. Again, I'm using the language in the discrete framework. We're going to soon extend that to continuous, but it's easier to understand it when you start with the discrete. Okay. Now, given that A is an event, probability of S is equal to 1, probability of the event needs to be between 0 to 1. Okay, it can be as low as 0, it can be as high as 1, but it can't be less than 0, it can't be greater than 1. Probability of A complement is equal to 1 minus probability of A. Because we understand that A complement and A are mutually exclusive because they're the complement of each other, they should be collectively exhaustive because together they make up the sample space. Because A complement was defined as everything that is not in A that is a part of the sample space. Okay. Now, for two events, suppose I take two events. Oh, and the next one is also fairly elementary. If B is a subset of A, probability of B should be less than or equal to probability of A. Okay? Okay. If you take any two events, call them A and B, then the union of probability of A and probability of B should be nothing but the sum of the two probabilities minus the intersection of the two probabilities. Okay? So what do we mean by union in simple language? Elements occur in both of them. But suppose I told you A is an event and B is an event. What is the probability of A union B? What am I trying to capture? We are not trying to capture the intersection of A and B. We are trying to capture either or. You're saying if A or B can happen, right? So you're trying to capture that or condition. So if you're trying to capture that or condition, why can't I just simply take probability of A and add it to probability of B? Why do I need to do anything more messy, like taking away the intersection? The intersection is kind of like double counting, right? So in some sense, I might say a randomly selected student from this class. I might be interested in two events, right? So one event could be their gender, which is the person male or female. The other could be, for instance, are they undergraduate or postgraduate? So both of these have two probabilities, and think about it, right? Both of these probabilities can add up to being greater than 1. So obviously, that itself tells you adding does not make sense. And if you're trying to capture that subset of people who are either male or postgraduate, the problem was that some set of these people were male and postgraduate both. So you can't count them 2 times. So what you do is you count them both individually, take those ones that you double counted and just exclude them separately. So understandably, if something is mutually exclusive, which means that the intersection is 0, you can just add the 2 events. Suppose I told you there was nobody in this class who's male and postgraduate, I should be able to just add the probability of being male and postgraduate, and that should give me the OR condition in some sense. Okay. Now, if they're mutually exclusive, that makes sense. Now, what if B is a subset of A? Again, the formula still makes sense, but if B is a subset of A, what would happen to this formula? The P of A intersection, so B is a subset of A, so A intersection B would be P of B. So it's like adding P of B and subtracting P of B, and you're reporting only P of A, which also makes sense because the OR condition should be only P of A because B was anyway a subset of A, right? Okay. Okay. Now we're going to introduce a concept called conditional probability. Okay. With conditional probability, often we don't like to just talk about the probability of B, right, some event. We'd like to talk about the probability of an event when you have additional information, right? When you already know something else. Conditioned on the fact that A has happened, what is the probability of B? Conditioned on the fact that A is true, what is the probability of B? Okay? So the simple idea behind that is probability of B given A can be characterized by the intersection of A and B, right? Because think about it. First of all, for probability of B given A, that means you're saying what's the probability of B happening, but you don't care about only when B happens. You know that A has happened. So the only things that you can count are the things where A and B have happened. Is this concept clear? So you're saying, given that A has happened, what's the probability of B? But thank you for telling me that A has happened, which means that the things that I can count as a part of this are the cases where B and A have happened. I take those things, but can I just count those things and say that's the set? Not really, because I need to normalize it by the fact that A has happened. Because B intersection A can be a very small thing, right? But I'm not interested in when only B intersection A happens out of the entire universe. I'm interested in B intersection A happening only when A has happened. So you need to boost that A intersection B for only the cases where A has already happened. Okay, so you divide by probability of A. Now this is again called the multiplication rule, where all you do is just have the basic algebra of moving P of A in the denominator over to the other side. And given that P of A intersection B is no different from P of B intersection A, it's the same concept. A and B need to happen. You can rewrite this in another form. Now we say two events are independent if often the only form that is shown is if P of A intersection B is equal to P of A times P of B. But the intuitive way, for me at least, is to think of it as if you're telling me that the conditional probability on B, that probability of B given A, is actually equal to P of B, right? You're basically saying the fact that A has happened or not makes no difference to the probability of B. So once you have this, right, then it just becomes algebra to show that this condition needs to be met, right? Because you'll just substitute P of B given A as, so you already know that P of A intersection B is equal to P of B given A times P of A. Where did we get that from? We got that from right here. And now you just substitute P of B given A by P of B, right? Then you have the first form. But it's always intuitive for me to think of it in this form or in this form here. You're basically saying the presence or absence of the truth of another event happening has not changed my view of what is happening to this event. So therefore, they must be independent of each other. Okay. Okay, so just building from this multiplication rule is what we call Bayes' theorem. And Bayes' theorem basically just says, just takes this formulation and just shuffles it around. And it turns out that this is very useful in many settings. Often we are interested in probability of A given B, but that's not how our data or knowledge base is. What we know instead is P of B given A. And we look at that in a little more detail in some of the tutorial problems, where in the real world you're always given one form, but you're interested in the other form, but you can go back and forth between the two through this little piece of algebra here. Okay. Okay, so now we're ready for the next step. So we've defined sample spaces, events, probability of events with respect to random experiments. So now we're going to go to the next step of defining something called a random variable. Okay? A random variable is a variable, this is a very, very high level, whose possible values are subject to variations due to randomness. Okay? So the variable takes on values which are subject to variations due to randomness. Now, the random variable has a probability distribution which is nothing but a mathematical function that quantifies the likelihood. And in brackets, I've said absolute or relative, and that's going to come in the next slide. We're going to talk about discrete and continuous again. But you just focus on the content without the bracket. You can think of it as a mathematical function which quantifies the likelihood of outcomes in the sample space. So you have a sample space, and you want to quantify the likelihood of the outcomes in the sample space. You want to use a random variable. So how is this different from anything that we've been talking about? Well, up till now, we were only talking about outcomes and probabilities associated with those outcomes. But now you're talking about a mathematical function that you can use to map the outcomes to the probabilities. Okay? But the outcomes to the probabilities mapping can be absolute or relative. Okay? And in a second, we're going to talk about what that means to call it absolute or relative. Now, obviously, this doesn't work, right? This doesn't work if your outcomes themselves can't be quantified in a numerical way. If all I was doing was talking about the outcomes as a blue or green or something like that, you can still have probabilities, you can still have a probability distribution. But this mathematical function that I'm talking about, which maps the outcomes, so I'm going to call the outcomes x. So I'm going to call these outcomes as something x. Then I'm talking about a random variable as something f of x, right? I should be able to use that f of x and get you the likelihoods. So x obviously has to be something that I can plug into f of x. Right? So if f of x is a mathematical function, I need x to be in that form, in the form of numbers on the real number line or something like that. Okay. Now, we can make the distinction between something called a discrete random variable and a continuous random variable. You remember how we spoke about a discrete sample space and a continuous sample space? We're going to use that same mapping to understand these two different kinds of random variables. So a discrete random variable is one with a finite or countably infinite, and this is a very important point, range. Okay? Here, you have something called the probability mass function. This is that f of x, that random variable we're talking about, which reflects the probability that a specific value or a countable set of values can occur. Okay? Okay. So what does this mean? I give you something called x. These are the outcomes. A probability mass function should be some f of x such that for each outcome, I should be able to plug in that outcome. So the outcome can be 0, 1, 2, 3, or something like that. I should be able to plug in those outcomes into f of x. And what should I get back? The absolute or exact probability associated with those outcomes. Okay, that's what a probability mass function is. If I give you the independent outcomes from the sample space, for anything in the sample space, that value x, I should be able to plug it into f of x, and what do I get back? The probability that that x could have occurred. Okay, so you go back to the example of the number of questions out of the 5 questions that you got right. The sample space was 0, 1, 2, 3, 4, 5. I should be able to plug in any of those and get an outcome, which tells me the probability of it. So I need a function like that. But that function also has to conform to a bunch of things, right? I should be able to add up all those probabilities. It should add to 1, blah, blah. Okay, now let's look at another conception, which is the continuous random variable. Now the continuous random variable is a different beast, okay? It is one with an interval. That interval itself can be finite or infinite, but within that interval, you have infinite possible values. It's an interval of real numbers for its range, and that's essentially what you're capturing. Here the probability density function, remember it's got a different name. It's no longer called probability mass function, it's called probability density function. This probability density function reflects the probability of occurrence within a given range or interval. So the only thing that I'm telling you is that the probability that it can occur within this range or interval is a certain value. So I'll tell you what it's not. Suppose you had f of x, which is your PDF, your probability density function, okay? And you had a particular value x. Suppose you go substitute x in f of x. You're going to get a number. You have to get a number, right? Because f of x is a function. Whether you like it or not, if you go substitute a value of x, you're going to get a number, and that number need not be 0. It's going to be some number. Is that number the probability that you can get x? No. That is not what a PDF means. Okay? The PDF, that is what a PMF means. A PDF only tells you, PDF is not supposed to tell you the probability of a specific outcome. It's supposed to tell you the probability of getting something in a range. How we can use the PDF to figure out the probability of a range, we're going to come to in a second.